Hey everyone, this is 2-6. We are looking at geometric proofs today. One thing that I just want you to make sure that you are aware of is, I know I said this in class, but that this is a very difficult topic. And please know that I am not looking for perfection right off the bat. I am looking for an attempt. I am looking for you to put forth full effort. I'm not looking for you to get everything right now. So if you are having trouble with this topic, I want you to breathe. You will be fine. I promise that I will take care of you. Okay. But it is a challenging topic is to start to understand proofs. Okay. The first thing we're going to talk about is what is a proof? Well, we talked a little bit in the last lesson about algebraic proofs where we had, we were solving an equation and we were writing the reason for each step. It's going to be similar to that, except that we are looking heavier in the geometry and then rather than the algebra. So most of our geometric proofs are going to be what we call a two-column proof. There will be a left-hand column full of statements, which was, if we think back about the algebra proofs, it was all of the equation piece of it. And then the right column will be the reason. So why do you go from one step to the next? Tomorrow in the next lesson, we will look at two more types of proofs, but for today, we're just going to stick with the two-column. So we are getting our first theorem today. We are getting the linear pair theorem. One thing that I want to kind of highlight here before we even get started talking about this is number one, all of the theorems in the book are going to have a number. I want you to completely ignore that number. We do not care about it at all because all it's saying, like this particular number, this is chapter 2, section 6, the first theorem. These numbers literally change with every single book that there is. So I am not worried about you ever memorizing a number. Please do not take any time looking at the numbers, okay? What you really want to look at is the title and what it says. You are never going to be required to memorize a title. You can always write in your proofs what the theorem says rather than what the title is. But if you want to use the title, that is absolutely fine as well. All right. So when we've talked about postulates so far, which are things that we cannot prove. So for example, we had that through any 2 points, there is exactly one line, right? That was one of the postulates that sets the boundaries and the rules for our space. And again, in our space here, we're using a cubic space. With other spaces, the postulates change because the rules are changing. And I just want you to know that like when we start talking about theorems, which we're going to get today, a theorem is something we can prove. So that is the difference between a postulate and a theorem. A postulate is something that we cannot prove. A theorem is something we can. So the first theorem that we are going to look at is the linear pair theorem. Okay, let's remind ourselves that a linear pair of angles are two adjacent angles whose non-common sides are opposite rays. They're two adjacent angles that form a line. Okay, so the linear pair theorem tells me that if I have a linear pair of angles, then they are supplementary. All right. Remember that if we're looking at this, linear pair means they're supplementary. Supplementary means they add to 180. So if I tell you this is a linear pair, I don't want you to say automatically that they add to 180. I want you to think about they're supplementary by the theorem, and then they add to 180 degrees. There is another step kind of in between that thought process. So it is important that you're kind of aware of what is going on there. Just so that way you're getting used to the way that proofs are kind of going to work and those little thought processes. Geometric proofs are logic. It's trying to figure out how you get from point A to point B and all the reasons why. So think of it like the old experiments where somebody was giving directions blindfolded to somebody else on how to make a peanut butter and jelly sandwich, and they forgot to tell them to open the bread, so that way all of the peanut butter and jelly ended up on the bag because they didn't tell them to take the bread out of the bag. Okay, well, geometric proofs are making sure we hit every step of making that peanut butter and jelly sandwich. So the big thing is not to skip any steps. All right. So let's take a look at an example. Now, with this example, please know that this one is a little more complicated than what we would normally ask of you, which is why we have some options here for what you're going to be plugging in. The second half, though, is a little more normal, but the front half is actually a little more challenging than I would expect from you guys. So when we have a proof, we're going to have a given statement and a prove statement. Whatever is given is going to go in that left-hand statement column. So I have that MJK and MJL are linear pair of angles. Well, so when I look here, where did that come from? They were given. Okay, now, what does it mean to be a linear pair? Again, a linear pair of angles are angles that are adjacent and whose non-common sides are opposite rays. So the sides that they don't share are opposite rays. So look what's happening here. Ray JL and ray JK are opposite rays. Well, how did I know that they're opposite rays? They're a linear pair. Linear pair told me opposite rays because that's what it means to be a linear pair. So I use the definition. Okay. Well, what do opposite rays tell me? Opposite rays tell me that they form a straight line. So we're going to use the definition of opposite rays. Okay. Now, there is technically a step that should be in right here where I have if they form a straight line, then they are a straight angle by definition of a straight line. And then we can say, okay, well, then the measure of that angle has to be 180 degrees because that's what it means to be a straight angle. Okay, so there really is like a little step skipped in here. Now, these steps are steps that I would expect you to be able to pull out here moving forward. Okay, again, things are still going to be a little challenging right now, and that's okay. But the bottom three steps are steps that are ones that you're more likely to see. This piece here, where we're defining the linear pair and using the definition of opposite rays, that is not something that you're going to see very frequently at all, if ever again, really right after this. All right, so when I look at step 5, I see that I'm taking MJK, which is this angle here, MJL, which is this angle here, and that is equal to LJK, which is the whole angle. So I'm adding the two angles together, setting it equal to being the whole thing. I am adding angles, so that is my angle addition postulate. Okay? Now, I know that LJK measures 180, so I'm going to take this 180 and I'm going to plug it in for LJK. So that is my substitution. All right, then from here, I have these two angles add to 180, which means they are supplementary. Again, that's what it means to be supplementary, so we're using the definition of supplementary. Okay, so this is what a proof looks like. Okay, again, these first couple of steps are a little wonky, but the bottom steps are something that is more likely to be seen. With this one is a little more challenging simply because we're proving the linear pair theorem, which we were just told in the slide before. So the nice thing is the reason we use theorems is because now I can go from this step straight to this step by using the theorem. I skip all of these 5 steps in the middle. I don't have to do them anymore because I can say, hey, they're a linear pair, so they're supplementary. That's what that's what using that theorem does for us, is that it cuts out all those extra steps in our proof. All right. Let's talk about our next set of theorems. Okay. I have a right angle congruence theorem. I'm going to kind of start in the middle here, which should make sense. Okay, if I have a right angle, I know it measures 90. If I have another right angle, it's going to measure 90. If I have another right angle, it's going to measure 90. All of those angle measures are the same, so they are all going to be congruent. Okay? So again, you can either write in your reasons right angle congruence theorem or all right angles are congruent. I tend to write this, but that's just me. You can do either one. Now, for the congruent supplements and the congruent complements theorem. All right, what we're going to look at with these is if I have an angle that measures 50 degrees, and I tell you that I have an angle that is supplementary to it. Okay, well, what angle is this going to measure? And you should hopefully be saying 130 degrees right now, because these are going to add to 180. Well, let's say I have another angle that is supplementary to that angle, and I want to know what that angle is going to measure. Well, it should also be 130 degrees. 180 minus 50 doesn't change no matter how many times we do it. All right, so then what do you notice about these two angles is that they're going to be the same. All right, that's all your congruent supplements theorem is saying. Complements is going to be the same thing, except instead of 50 and 130, it would be 50 and these would be 40. All right, so anytime we have two angles that are supplementary to the same angle, those angles have to be congruent. Or if they're complementary to the same angles, then these angles would have to be congruent, depending on whether we're looking at 180 or 90. All right. This isn't going to be a super heavy theorem that we're going to see, but I do want you to be aware of it and know that it's there. Again, the biggest thing is it does save us some steps in a proof. All right, so let's take a look at example 2. Okay, I want to write a 2-column proof. Now, this is going to be something more like what you're going to get used to seeing. What I want you to look at is before you even start the proof, I want you to look at what you're given, and I want you to look at where you're trying to go. This needs to make sense. So if I notice that A and B are supplementary, I'm told that A is 45 degrees. You want to know, does it make sense that angle B is 135? And hopefully that answer is yes, it does, because those two numbers are going to add to 180, which is going to give us that supplementary. All right. So we're going to start in this case with writing all of our givens in one step. Okay. So you're always going to write your givens in your statement side, and then your reason for those specific ones are going to be given. You need to make sure that it is exactly what is in your given that is going to be, or get the reason of given. Okay. And sometimes they're in one step, and sometimes they're in more than one step, which we'll kind of look at here in a second. Either one is perfectly correct. You can always write all of your givens in one step. All right. But let's take a look here. We're told angles A and B are supplementary. Well, what does that mean? Okay, what does supplementary mean? Right, it means that those angles are going to be adding to 180 degrees. So I'm going to write the measure of angle A plus the measure of angle B is equal to 180. So now the question is, why? Well, what word up here told us this was true? Supplementary. It means that they are going to add to 180. So because it's what it means, it is the definition of supplementary. All right. Now, I'm told that A measures 45 degrees. So in order to get that B is 135, I need to plug A in. So I'm going to get 45 plus the measure of angle B equals 180 degrees. So I substitute it into here. Okay, from here, in order to solve, I need to subtract 45 from both sides. So it is subtraction. A reminder, can't spell. A reminder that when you're abbreviating subtraction and substitution, that you need at least 4 letters, because you cannot abbreviate as SUB. Okay, because I don't know which one you mean. All right, so if you have any questions on that, make sure you make a note of them somewhere. All right, let's take a look at another example. Again, I want to start by looking through what we're given and what we're trying to prove and make sure that it makes sense. Okay, so if B is the midpoint of AC, does it make sense that I've got a midpoint that I know these pieces are congruent? Okay, so if these two pieces are going to be the same because B is a midpoint. Well, we're also given that AB is congruent to EF. So if these two are congruent and these two are congruent, hopefully it makes sense that all three pieces are congruent, which is what we're trying to show. We're trying to show that BC and EF are also congruent. Okay, so hopefully that makes sense. Again, you kind of want to start there so you know what you're doing. Now, notice all the reasons are empty this time. So I'm going to find B is the midpoint of AC, and I'm going to write given for that reason. I'm also going to find AB is congruent to EF. Well, it's down here in step 3. I'm going to write given for that one. So I'm really only trying to find 2 reasons for this proof. Okay? Well, what did we say it meant to be a midpoint? Okay, midpoint is in the middle, so it bisects the segment, so I've got 2 congruent segments. Okay, so what word here told me that those pieces were congruent? Okay, midpoint told us that these were congruent. So that is our definition of a midpoint. Okay, now I have that AB is congruent to EF because it was given to us. So what I have here is AB is congruent to BC. AB is also congruent to EF. So these are both congruent to AB, which means they are congruent to each other. That is our transitive property of congruence. Okay. Now, one thing that I want to kind of talk about here. Let's pretend for a second that this was AB equaled BC, AB equaled EF, and you don't need to write this down on your notes, okay? We're just going to talk about it for a second. And BC was equal to EF, okay? If we had this, it would still be transitive, but I could also say, well, if AB is equal to BC, I'm going to plug BC in for AB, and I can say substitution. So when I have equal signs and I have a transitive property, substitution works as well. There are times that substitution does not, or transitive does not work for substitution, but substitution can always work for transitive, again, only when I have equal signs. Because I can substitute in numbers, I do not substitute in figures. When I have congruent symbols and segments like I do here, then it has to be transitive because we don't have a transitive property or a substitution property of congruence. We only have a substitution property of equality. We do have a transitive property of congruence. All right, so that's why this one has to be transitive. All right, let's do one more. All right, so our plan is to write a 2-column proof again. And again, I want you to look at the information that you're given. We're given angles 1 and 2 are supplementary, and 1 is congruent to 3. We are trying to prove that 2 and 3 are also supplementary. So again, you don't have to write these numbers down. In fact, don't, because I'm going to erase them fairly quickly. If this is 50 degrees, then this has to be 130 because they're supplementary. Well, if 1 and 3 are congruent, this is 50 as well, which makes these also supplementary. So hopefully that makes sense in terms of where we're kind of going with this. Now, you will notice that this proof has a plan for the proof. All the plan is just like a general guideline of where you're going to be going. So if you get stuck and your proof has a plan, then you can start looking at that plan to kind of help you figure out where you're going. All right. So the plan is we're going to use the definitions of supplementary and congruent angles, and then we're going to use substitution to show that the measure of angle 2 or measure of angle 3 plus the measure of angle 2 equals 180 degrees. All right. So let's talk here. We have angles 1 and 2 are supplementary. What does it mean to be supplementary? It means that those measures are going to add to 180 degrees. So I'm going to do the measure of angle 1 plus the measure of angle 2 equals 180 degrees. Again, we know that from the word supplementary. That is our definition of supplementary. Okay? Next, my angle measures are congruent, which means, my angles are congruent, which means the measures of my angles are equal. Okay, so anytime we're going from angles are congruent to their measures are equal, or segments are congruent to their measures are equal, or back in the other way. If I go equal to congruent, it works here too. This is always the definition of congruence. Okay, so it doesn't matter if we're going congruent to equal or equal to congruent. Anytime we're transitioning back and forth between those, we're using definition of congruence, because the definition of congruent is two figures that have the same measure. All right, so that is why it doesn't matter if we're going forwards or backwards or which way. Anytime you're going back and forth between equal and congruent, it is definition of congruence. Definition of equality is not a thing. Okay, so please make sure it is your definition of congruence. Now, I want to get 3 into our supplementary. So that means I need to get 3 in here somewhere. So I am going to, since 3 and 1 are equal, I'm going to substitute in. So I'm going to have the measure of angle 3 plus the measure of angle 2 is equal to 180 degrees. Again, I substituted angle 3 in for angle 1. Now, from here, I have 2 angles add to 180, so therefore I know that they're supplementary. Again, that is my definition of supplementary. Okay, so it's important that you see that I can say, hey, they're supplementary, so they add to 180, or I can say they're 180, so they are supplementary. Either way, that's definition of supplementary. So it doesn't matter if we're going from the words to the equation or the equations to the words. Both of those are definition of supplementary. Okay, now, when you are doing your homework for this section, it is really important that you write down all of what's given to you, the proof statement, the given statement, the pictures, and the entire proof. Okay? This is the one time that I ask you to copy your problems from the book. Okay? Usually I'm just asking you to show your work. But for any time you have a proof, I want your homework to look like the notes in your that you're looking at right now. They need to look like your notes. You need to have every given statement written down, every proof statement written down, every picture copied, and then underneath that, have your T-chart with your statements and your reasons. All right, one of the things that I do is I know if I'm filling this in, I'm going to put a box around it. So that way when we're checking our homework tomorrow, we have the ability to, you can see really quickly which ones you were checking and which ones were just copied in. Okay, so, but you need to know that you have to copy everything, because right now on your tests and quizzes, all of your proofs are going to come from something that you've already seen, whether that is your notes or your homeworks. Okay, any geometric proof is going to be something you've already seen. All right, so keep that in mind. That is why I want you to draw everything out. If you have a plan, you do not need to copy the plan. Okay, just the given and the proof, the picture, and the table. The plan is the only thing that you can skip copying, but otherwise you should copy everything else. All right, so this is what you should be working on for your homework, and then I will see you guys tomorrow. Have a wonderful evening.